Luckily, we have Tengyu Ma from Stanford. Tengyu's been working on deep learning theory for a long time, and now also deep learning startup practice.
Okay.
Take it away, Tengyu.
Okay, thanks. Thanks for coming. Thanks for the introduction. Yeah, it's good to see you, folks. I guess I'm going to talk about contrastive learning, actually. So I changed the title to make it closer to the topic of this workshop. So I guess this is probably a kind of like a stretch in terms of the definition of generalization. So basically, we're going to talk about why you can pre-train the models and it still works on the downstream tasks. And I kind of call that generalization. So I guess I'll keep the motivation very short. So you probably know that, like AI is undergoing a paradigm shift, actually probably has already undergone the paradigm shift. So we are training these large models, GPT-3, GPT-4, and they work for a wide range of downstream tasks. I guess we wrote this paper, foundation model, white paper, which is just a survey paper. And these days, every model is kind of like, most of the new technology is based on the foundation models. So I guess, and what's the underlying technology? I think I'm going to introduce the pre-training a little bit. So when you say pre-training representation, it means that you map this data into, for example, vectors. And these vectors are representations of the data. And sometimes you call this representation, sometimes you call this embedding, sometimes you call this feature extractor. And the point here is that you learn these representations from unlabeled data. And then you adapt these representations to downstream tasks. For example, you can do a linear classification on top of representations on some labeled downstream tasks. You have like +1, -1 as labels, and then you learn linear classifier in the representation space. Another application could be that you do a k-nearest neighbor search with embeddings for semantic retrieval. So for example, you are given one image and you can search for related images by doing a k-nearest neighbor search. And this is actually one of the pretty popular applications these days in the so-called retrieval augmented generation stack, which has been widely used in most of the AI startups in the Silicon Valley. So basically, you want to build a chatbot. And what you do is you say you're going to start with the retrieval process. So you retrieve from unstructured proprietary data some relevant information first, and then you give this relevant information to large language model as context. So basically, given a query, whatever questions you have, and then you first retrieve from the company's knowledge base some relevant documents, and then you give all of these documents and the query together to the large language model, and then the large language model becomes more factual and more reliable. And the retrieval step is done with these embeddings, where you first vectorize every documents in your database, and then you vectorize your query, and then you look at the k-nearest neighbors of the query and see which one are the relevant documents in your database. So it's called retrieval, and the whole stack is called retrieval augmented generation. I think that's the most that's kind of the predominant approach for enterprise AI these days. And of course, there are many other ways to use these models, pre-trained models. I think these days actually the representations are less. Not many people are using this linear classification anymore, right? These days, 2 years ago, we are talking about fine-tuning linear classification on top of representations, and right now these days, I think you basically just only do zero shot. So basically, for most large language models, you just can prompt, unless you are doing the retrieval step. So without the retrieval step, if you don't need any proprietary information to assist the large language model, then you just do zero shot and instruct it with the right prompt. Even in context learning is but less needed these days from what I see to some degree. But generally, I think this the question is about how do you use these pre-trained models for downstream tasks? And here in this talk, I'm only focusing on this kind of like linear classifications on top of representations. So I guess what are the theoretical questions here, right? So I think the theoretical questions for me was that why you can pre-train on unlabeled data, but it helps a wide range of tasks. You only have one pre-training loss, which is some kind of self-supervised loss functions, maybe next word prediction problem, maybe like a contrastive learning, which is what I'm going to talk about. But why this single loss function can help such a wide range of tasks? And what's special about that loss function? And what are the features here, right? So so it turns out that if you use pre-training, you are more label efficient because you need 0 labels in the pre-training phase, and then in the adaptation phase you can use small number of labels. Sometimes you have 0 labels as well in the adaptation phase if you do 0 shot. So and as I said, the loss function seems to be universal to the downstream task. There are only probably 2 loss functions. One is the next word prediction loss function. The other is contrastive learning, which is for embeddings. And also, the pre-training makes it much more robust against domain shift. And on a more kind of like technical level, I think the key technical question I was always kind of struggling with is that, how do you kind of like go beyond the classical theory? At least it sounds like you need a different theory, because you need a lot of different training and test tasks. So most of the classical domain adaptation theory says that the training task is a supervised task and test task is also supervised task. But here, the training task is, the pre-training task is unsupervised, and test task could be supervised or unsupervised. And another challenge was that, to me, is that how do you kind of disentangle this with other complicated questions in deep learning, right? So you have the architecture, the nonlinearity, the optimization, non-convex optimization, all of this, right? So you want to allow the theory to handle nonlinear models, of course, but also you don't want it to be kind of like too dependent on the nonlinearities, because once you are talking about how do I optimize the non-convex loss functions of this pre-training next word prediction loss or contrastive loss, then it's kind of like in some sense, you are solving 2 challenging questions at the same time. Like you have the question about the loss function, also you have the question about non-convex optimization, and maybe you have some other issues with the expressivity, all of this together, right? I'm going to touch on some of this later in the later part of the talk, but actually, in some sense, you see that once all of this get putting together, it's kind of very complicated and it's very hard to build a very clean theory. So how do we kind of like abstract away some aspects that are already hard in supervised learning is kind of like one of the key challenges that I think we are facing here. Like the first part of the talk is trying to provide some kind of clean abstraction so that we can study the loss separate with the other parts. But later I'm gonna kind of put things together a little bit because the clean abstraction still has some limitations in some sense. You'll see. So going towards how do I isolate, addressing this kind of question, like let me give you some preview on how I was thinking about this. So you want to isolate the role of the loss. With, for example, polynomial data. So the typical pipeline is that the eventual target you want to answer is that the eventual scenario you want to analyze is that you have an empirical pre-train loss, and you train some parameter, say the hat, from this loss function, and then you do some kind of like a linear hat. You optimize, let's call the linear hat gamma, and you optimize the empirical downstream loss function, which is a function of both the theta hat and gamma. Theta hat is the pre-trained model, the base model, like say a transformer, and then gamma is the linear hat on top of that. So right, and here you're only optimizing gamma, you're fixing theta hat, and here you're optimizing theta. And you want to know that why this part helps this part. So, I think the first thing is that maybe let's just assume that you have sufficient data. And sufficient means that you have polynomial data that is a polynomial in the model class complexity, so that you don't have to worry too much about this generalization. So basically, this is pretty much the only generalization I'm doing in this talk. So the empirical pre-train loss is close to a population pre-train loss. And this is not too crazy of an assumption to start with, because actually empirically it's kind of true for this scale. Well, when you have like 20 trillion tokens these days for pre-training, the empirical pre-training loss is very close to a population pre-training loss. Like you don't even go through the entire data set once, just because you don't have enough compute. So there's no way that you can overfit in this regime. So it's probably fine to just assume that you have population pre-train loss. At least assume that you have sufficient data to at least for theoretical purpose, that's probably a reasonable starting point. And then because here in this second phase, you're optimizing only a linear hat gamma, which is also a small number, of parameters. It's often like maybe gamma is like 4,000 dimensions. So this is also kind of true. Because you may have like maybe 10K examples for the downstream tasks, and the empirical downstream loss is close to a population downstream loss. So basically with this abstraction, then you only have to worry about the population to population transfer or generalization, whatever you call it. So why the training on pre-training population pre-train loss will transfers to performance on the population downstream loss. So and given that this is assuming polynomial data, but polynomial data is the same as infinite data. So why not just assume it's infinite data? And the question just become as I alluded to, like how does theta hat ensures that there exists? Oh, something wrong with my. Okay, so the question is that how does theta hat? How does the pre-trained model ensure that there exists a linear hat gamma that minimize the downstream loss, right? So if there's no gamma such that this is small, then your pre-training was not useful. But if there exists a gamma, then the pre-training was very useful. And in other words, for this kind of like linear classification case, basically it's just asking why does pre-trained representation are linearly separable? If they are linearly separable, then you can find that linear separator with a reasonable amount of data. So basically, it's all about the structural relationship between pre-training loss and downstream loss. And kind of the high-level thing is that the pre-training loss will ensure that there's some structures of the unlabeled data got encoded in the representation theta hat. And this encoding is actually in some sense linear. That's what we need to justify. And then once you show this, then this is pretty easy because basically you are saying that any tasks whose labels depends on the same structure will be able to will get solved. If your tasks are not depending on the same structure, then of course you cannot solve them. I'll give one example here in a moment. So here's the outline of the rest of the talk. I'm going to start talking about the contrastive loss, which instantiates the plan, and then the section 2 and section 3 of the talk is about how do we think about some of the more complex issues like inductive bias, expressivities, implicit bias of the optimizer, so on and so forth. Okay, so let me just introduce contrastive loss very quickly. I assume some of you already heard of it a lot. So the principle of contrastive learning is that you want to define these positive pairs, and in images they are augmentations of the same image, and you want the positive pairs to have close representations. For example, you have augmentations of the same dog, and then you want the representations of these two augmentations to be close to each other. And they also define so-called negative pairs, which are just random pairs of images, the augmentations of random pairs of images. For example, this and this would be a negative pair, and you want their representations to be as far away from each other as possible. But note that we don't know which image is a dog and which image is a cat. This is unsupervised learning, no labels. So the negative pairs could do some damage, a small amount of damage, because you could have these two dogs which are supposed to be semantically very related, and their augmentations will be considered as a negative pair as well, because they are augmentations of different image, and you're going to push away their representations as well in the loss function. So basically, the loss function. So this is a good thing for the loss function to do. This is a good thing for the loss function to do. And these two things are the collateral damage because you don't know what the content of images are. And in some sense, you are trying to show that the damage you make is not big enough compared to the benefit of the other two forces you are enforcing. So basically, there are many different ways to try to encourage the close representation of the positive pair and these distant representations of the negative pairs. I'm not going to go into the details about the exact loss functions. There are a bunch of them, like same clear, same SAM, so on and so forth. But they are all using the same principle. And for this talk, we don't necessarily care about the exact details about the loss functions. So the general kind of like argument here is that if you do contrastive learning on infinite or polynomial data, then you are going to be, this is just a preview, I'm going to expand on this. So it's going to be equivalent to spectral clustering on infinite graph, which I'm going to define. And then because you are doing spectral clustering on this infinite graph, you can naturally get that Euclidean structure in the representation space is pretty close to the clustering structure in the graph. And then you say that every downstream task that are compatible with the clustering structure will be solved by your representation. And that's how you kind of like kind of scoping it, right? So there's no way you can solve all the possible downstream tasks. You can only solve downstream tasks that are compatible with these clustering structures in a graph that I'm going to define. So what's the graph? This is the key concept in this talk. So this is so-called population positive paragraph. So I'm stressing the word population because I'm working with all possible images. So basically, imagine that you have a graph. The vertex set is all possible images in this world, and including like any reasonable images, not like images on the web, but just all possible images that are in the support of the manifold of images. And you have an edge of two images if so there are all images that are all image patches, means like augmentations of the images. So basically, every node is augmentation of some images. And you have two nodes got connected if they are augmentations of the same image. And otherwise, you don't connect them. So basically, if they share the original image, then they are positive pairs, and otherwise they are negative pairs. And you can see that because it's very unlikely for two images to be augmentations of the same image, this graph is extremely sparse. And also it's extremely big because it contains all the possible images, right? So it's a very, very sparse graph and extremely huge, exponentially big. But we don't claim that there are some structures in this graph, which are some clustering structure here. So the claim is that if you have two images that are about different semantics, right? Maybe a bulldog and a cat, then their distance in this graph is very, very big, just because that there's no way you can go from this image to the other image by just doing augmentations, right? So you probably, no matter how you augment this cat, you wouldn't get to the dog. At least it's going to be very difficult.
Exactly how you discretize images, right? Because two different patches, if you have very high precision of the color, they're very unlikely to be patches of two different images.
Oh, that is not a problem, because when you do the augmentations, actually they are also some small Gaussian blurring. So which kind of like make.
You will have like this cat and this dog maybe share the same patch.
No, a cat and dog cannot share the same patch because the Gaussian blurring is too small, so that there's no way you can do that. But at least it removes the problem with the precision. So if you have two dogs that are just extremely close, they're like, for example, their L2 distance is epsilon, then they could be pairs. They could be augmentations of each other.
Two different images can share the same patch, right? Because of blurring. Because in principle, you can imagine two different images can never have exactly the same patch.
That's right. So two different images can have the same patch, but there is like if you have two completely different images, right? This one and this one, you basically say they cannot share the same patch, because the chance that they can get augmented into the same one is just too small. It's like maybe a double exponentially small or something like that. But if you have this image and the small, very, very small shift of the image, or maybe a small difference, like you have a very small changes in the pixel space, then you can say they are augmentations of each other. So the augmentation is a very, very local concept. So basically, you can maybe I'll get this in a moment. I'll have a slightly simplified version of this. But basically, like only images are very, very, very similar can be augmentations of each other.
Yeah. Like I'm trying to understand if the augmentation, you can have is the assumption that you're only augmenting the part of the image that is somehow very relevant to, because both cats on the same lawn, like if the patches are not really covering the main part, but like the grass, then you can have. I'm just trying to understand.
So a short answer is that augmentation is a very abstract concept here. So the theory works for any augmentations, in some sense, like but you want assumptions to make sense in some. So basically, exactly how do you do the augmentations is not a problem here. So basically, if you have a different augmentation, then you're gonna have a different graph. And if augmentation is too crazy, then your graph probably doesn't have a nice property, right? Suppose your augmentation is just that I'm gonna blur the image to basically out kind of pure noise. Then this will be a pure, fully connected graph, and there's no structure there, and there's nothing you can learn. So that's the downside of using a very, very big augmentation, which destroys all the structure. But if you use a very small augmentation, then the structure will be clearer. But then maybe there are other kind of downside of it. For example, you could if you just use, for example, L2 perturbation as the augmentation, then you're gonna have a clear structure, but maybe the number of clusters is too many, something like that. So there's some kind of balance between how strong the augmentations are. Does it make some sense?
So in the limit, you will have the number of clusters, which is just equal to the number of images, right? You can have very high.
There's even number of images here. This is a manifold.
So you'll have infinitely many. Each image will give you a little cluster. Because each image will be kind of almost unique.
Sure. Yeah. Maybe let me answer. I have one slide which makes it a little bit simpler, but maybe let me answer some other questions first.
Maybe I missed something, but could you back up a little bit to where you claim the downstream population equals to the population for the downstream? The empirical equals to the population.
Oh, that's okay. That's a few slides ago.
I could agree that, like, for pre-training, you can assume there are infinite data, but for downstream, I don't think we have.
Yeah, but the downstream you only optimize for a small number of parameters, gamma, for linear head, at least for the moment. If you do fine tuning, I think it's gonna be probably going to assume you use LoRa or something, so that you also don't overfit to the downstream. So at least that's the abstraction right now. Yeah. I think this. I think it's very useful to discuss this graph thing a little bit more. Maybe let me jump to this a little bit. So one of the situations that theory does apply to is the following situation. Let's say suppose your augmentation is a very small Gaussian perturbation. So there's no chance that you can augment with this augmentation. There's no way you can augment a cat to a dog. But you can augment a cat to a very, very nearby cat. And then the graph is really just the so-called proximity or geometric graph, which means that you just combine connecting nearby points. And in some sense, you are just drawing a manifold here in some sense. But even with this graph, you can believe that the cats are more connected to each other than from the dogs, right? So it's kind of harder. Like maybe this is a manifold for the cat and this is a manifold for the dog. And there's some very, very special cases where you have a dog and cat which looks some ambiguity, like where the dog is, it's both a dog or cat or something like that. And then you can probably have some edge here. But in most cases, you have a clear manifold here, a cluster and clear cluster here. So and in this case, but you can also add stronger augmentations, where you can augment a cat to even maybe the flip of the cat, right? Or maybe you can augment a cat with a rotation or maybe a translation of the cat, and that means that you are kind of like adding more longer distance kind of like edges in this graph. So the graph's connectivity becomes better. So at least the inter class kind of like connectivity will be better if you have a stronger augmentation. But of course, you don't want to say that you augment the graph so much so that you get edge from here to here. That would be a damage for the graph. So and the only assumption you make here is that no matter what augmentation you use, you want to make sure that the intra-connectivity is better than the interconnectivity, and that's how you get the structure. And in some sense, in this language, some of the early works in this area, including some of the Jason and Sanjeev's work, requires the cluster to be somewhat kind of like requires this graph to be somewhat kind of like a complete graph, and there's a little bit different structure than here. So maybe let me just go back to this just very quickly. So this slide is about a very special case where you have a Gaussian perturbation. And this slide is more about the real augmentation. And I think what I want to justify here is that within the cluster, you do have connectivities. Even the two dogs are very different. So that's what I'm trying to say here. So suppose you have a bulldog and you have another bulldog, and they can still be connected, even though the sequence may be very long. But you can still augment a little bit each time. Maybe you change the locally a little bit, you change the background a little bit, maybe you do some translation a little bit, and eventually you can augment to another bulldog. But it's very much harder to do this between a bulldog and cat.
Maybe I'm just to understand, is this the assumption that there exists a manifold in which the representations have the structure, or are we assuming because we don't know that the first image and the last image is of unsupervised.
Yep. The assumption is that if you build this graph, in your mind, conceptually, suppose you build this graph with the augmentation you care about in your mind, and then this graph will be having some kind of structures there, and and there could be even some kind of here I'm drawing some kind of hierarchical structure, right? You have some cat, and within the cat, there's probably 2 subclasses, and within the dogs, there are probably 3 subclasses, so on and so forth. Yeah. Cool. Okay, great. So assuming this, right? Assuming you have this graph built in your mind, and then assuming you have infinite data, you can prove that if you minimize the spectral contrastive loss, which I'm going to define, which is a special type of contrastive loss, it's going to be equivalent to the so-called spectral clustering on a positive paragraph up to some rotations. And there is rotations because the loss function is not enough to it's a rotational invariant, so there's no way you can recover the rotations. So, and the spectral contrastive loss is a loss function we define in this paper, which is a kind of like a simplification of some of the other more complex loss functions. So, so basically, it shares the same principle. So you have 2 parts of the loss function. The first part is that you have a positive pair x and x plus, and they are augmentations of the same image, and you want their correlation to be as big as possible because you have a minus in front of it. And the second part is x and x prime are negative pairs. They are augmentations of random pairs of images, and you want their correlations to be as small as possible because you have a square term here. So, so this is kind of like almost the same. At least it's instantiating the same principle of the contrastive loss, and we run experiments, and it still works, and it's actually in some cases it works better. The real loss function that people use in practice involves some exponentials. It's the same principle, but it involves exponentials and log loss, softmax, and so forth. In some sense, this is kind of a quadratic version of the logistic loss that people are using in practice. The logistic version, the version with log and the exponentials is too hard to analyze, and you break all the linear algebra. Yeah.
Is it the problem that there are many more negative pairs and positive, or is it doesn't matter?
They are indeed a lot more negative pairs than the positive, but you are sampling the pairs. So actually in practice you always have a like it's not like you have like a so the number of negative pairs is probably like exponentially more than the number of positive pairs in theory, but when you are sampling you'll probably have like a constant factor difference.
I'm trying to also still understand this, the issue that you're pointing out of like you could have 2 images of the same class, but because they are 2 different images, they are going to be considered as negative example here, right?
Yep.
So in a way, if there are many classes, you're better off than, let's say there were just 2 classes, then there would be a lot more examples that would be considered negative, which should not have been negative.
Yeah, that's true.
Versus because there is just lots of classes and few images per class, then it is better in this scenario, right? Because then any 2 examples you pick are very likely going to be from different classes.
I think you're also asking about the balance between positive pairs and negative pairs. I think that's kind of like addressed by choosing this constant, right? This is 2 and this is 1. I think that's addressed there.
No, I'm asking about the number of classes. Let's say you have n examples and k classes, right? Like the larger the k is, it seems to be better here. Because if I had just 2 classes, and then I pick.
Why? But because your argument is that the balance between the negative and positive pairs matters because the ratio between them depends on how many clusters you have, right? But the ratio between the positive and negative pairs are not that essential here because you take expectations here. It doesn't matter how many. The raw count doesn't really matter, right? You are sampling from the pairs. So the raw count between the positive and negative pairs, the ratio between the positive and negative pairs don't really matter because you are taking expectations here.
You mentioned this quadratic thing works better than exponential from industry people. Does it work better in terms of some downstream task or?
I don't think it works universally better. I think it probably my startup is using the exponential version, so so you can tell from the actions. But I think empirically, on the downstream tasks, we do at least in the context of this paper, we have done a lot of experiments, and they can be better. At least slightly better, or at least comparable, let's say. right? So and there are some benefits of them. Maybe I'll talk about that. So with this kind of like contrastive version, you can use a smaller batch because it's a clean definition of this. I guess probably I didn't talk about the exponential version where you have to put the positive pairs and negative pairs into a single batch, and often you need a very, very big batch, and actually that creates some of the system issue because you have to put all the batches on multiple GPUs and actually multiple nodes of GPUs, and there's communication issues, so on and so forth. So at least this one, this loss functions is insensitive to the batch size. It's expectation of these things, right? You can even sample one x and x plus, and you can train on that because it's a very clean formulation. So that's one thing, and we also don't need some of this momentum encoding in some of this BYOL MoCo stuff, and you don't need stop gradient in SimSam. But just to be clear, I think empirically, I think most people are still using SimClear. I think there has probably my understanding that SimClear has some robustness properties which make it more robust to certain kind of weird cases. And in this kind of like very academic environments, not all of this works pretty good, and we are probably working even at least better than SimClear. But when you have real cases, at least my team in my startup don't use this our version just because they don't risk the complications that they don't know. Yeah. Anyway, yeah. So cool. Any questions here before I proceed? Yeah.
So you assume this intra-cluster connectivity is larger than inter-cluster, right?
Yes.
That depends. That's determined by the strength of augmentation, right? So
Yes. Yes.
How do you choose augmentation strength in an unsupervised way?
Yeah, we don't know. Like this lays the framework for you to do it to choose the augmentation, because with this paper you say, okay, how do I choose augmentation? I choose augmentation to make the inter-class connectivity to be bigger than the inter-class connectivity. So you have an intermediate goal for you to optimize for the augmentation, but we didn't answer that question. We didn't answer how do you choose to optimize the connectivity.
Can you give some intuition why one of the terms is squared and the other one is not? Is there like a reason for that?
Maybe let me answer that in a moment when I derive the thing. But you need if there is no square, then this is gonna be negative, right? So like then you are doing the wrong thing. But I'll talk about that in a moment.
Is an easy way to make that 0 and make it more orthogonal?
Can I say again?
Is the square just an easy way to force that term to be 0 and thus promote that they are orthogonal?
It's a way to do that. Whether it's an easy way, I think you can say so. But it's definitely a way to do it to make it more orthogonal. That's definitely true.
So f is bounded in some way. Like, are you taking after the softmax?
F is bounded in the sense that no, F is not bounded. When you prove the bound, probably you need to assume F is bounded in somewhere. But at least there's no like at least at this moment we don't need to assume F is bounded. F is a vector. F outputs a vector.
Then can't they find situations where I make x and x prime orthogonal, and then I take the first term to minus infinity, and so then the loan becomes minus infinity?
Oh, I see. So let me think about. Okay, so maybe I misspoke. Let's see. So we probably have assumed that this is norm 1. The F is norm 1. Yeah. I think in this context, the norm F is norm 1. Yeah. Thanks. Okay. So so the question is how to. Okay. So next I'm going to talk about how to prove this, right? So why the spectral contrastive loss? Why this loss is the same as spectral clustering? Let me briefly review what spectral clustering is. Suppose you have a matrix, n by n adjacency matrix, which is kind of like a graph, the adjacency matrix for a graph, and n is the total number of all image patches in our case, which is exponentially big number. If you do spectral clustering on this graph, what you do is that you first take the top k eigenvectors of this n by n matrix, and you put them as the columns here, u1 up to uk, and then this is an n by k matrix. N is the first dimension, k the second dimension, and you look at the rows. So you have n of these rows, and each row will be the representation of the corresponding ith image. The ith row will be the corresponding representations of the ith image, and that's how you do contrast. This is exactly the spectral clustering algorithm. So and why they are the same? Here is the intuition, and I will probably talk about the square loss. So suppose you have a graph with, for example, 3 clusters, and they are completely isolated, And you have this eigenvectors. So this is the eigenvector formulation, right? So you take the rows of the VIs, which are the representation. And by some very simple calculation, using the Rayleigh quotients formulation of the eigenvectors, you can show that these VIs actually are the minimizers of this objective, where you are minimizing the distance between V and Vj, where I and j are the edges in the graph, and with the constraint that VIs are isotropic, meaning like this matrix is orthonormal matrix. It's the rows, the columns are orthogonal to each other, and the reason, and this objective is just some kind of like trace of the eigenvector matrix F times the Laplacian times the eigenvector matrix F, which is a quadratic form. So this is the basically the Rayleigh quotient to some. This is the Rayleigh quotient when you have vectors, when you have multiple dimensions of the multiple number of vectors. So basically you are minimizing the Rayleigh quotient with the constraint that actually the whole thing is the Rayleigh quotient. Anyways, you are minimizing this Laplacian form with respect to that VIs are isotropic, and this square is where we get the square term in the quadratic, because the cross term is the first term for the positive pair, and yeah, but to basically expand this, you're gonna get the contrastive loss. Yeah. So, and the contrastive loss is, you can see like in principle, they are doing exactly the same thing, right? You are just saying like for any edge ij, vi needs to be close to vj, and that's what exactly this is doing. And the only difference is that for the random pair, you are saying like vi is far away from a random vj, which is not exactly encoded here, but actually it's just like a different ways to write the diversity of the VIs. And you can just massage the calculation a little bit, and you found that these two are exactly equivalent.
Because in this formulation, there is no this far away constraint, right?
Oh, the formulation, yeah, in this formulation, there's no. Yes. Yes.
So where does this constraint? So constraint, I think you have to build the name, right?
Yes. So the constraint comes from this. The VI is also isotropic, and why you so VI is isotropic just means that the columns are orthogonal to each other, which just means that you have eigenvectors which are orthogonal to each other. So basically, when you have eigenvectors, the k eigenvectors have to be orthogonal to each other, and that means the columns are orthogonal, and that means the rows, the quadratic. The rows are isotropic. Isotropic just means that F transpose is identity. F transpose F is identity. That's exactly what this means. So
you think this plays the same role as
yes. Yes.
I think there is I have very similar critical question in there, because then in clustering like this, that you have like k clusters, and so that like in the unsupervised, is the assumption that you're kind of naturally finding the data is now getting clustered into these natural k clusters that exist in the data. Is that the way to?
Yes, exactly.
What's E?
Oh, what?
So its minimum over the sum by j belong to E was.
E is the set of the edges. Is the edge set of the graph. Yeah, sorry. Yeah. It's not entirely obvious why this is the case, but it's really just a very simple mathematical, like you just do a simple derivation. It's exactly equality. So okay, and so this is the first question: contrastive loss versus spectral clustering. And now the second question I'm going to answer is that why the downstream tasks can be solved linearly, because you just encode some of the structure, that's easy, but you need to encode them in a meaningful way so that you can extract the structure for the downstream task using a linear classifier, right? So that's the second theorem, which is that suppose the positive paragraph have, say, R major clusters. By major cluster, I mean that there's this interconnectivity versus interconnectivity constraint separation. And if your representation is bigger than 2R, your representation dimension is bigger than 2R, then you can prove that linear classification on the representations can be solved. Can solve, linear classification on its representation can solve any downstream tasks as long as in the downstream tasks each cluster has the same label. So you could have like probably 10 clusters and you group them into 2 labels. That's fine. But as long as every cluster within the cluster you have the same label, then that's a valid downstream task that you can solve with linear classification on the representations. And this the last blue part is just basically trying to stress that you need some relationship between the task labels and the structure of the pre-training data. And this proof is very simple, which is with very, very simple spectral graph theory tool. It's much easier than the analysis of the spectral graph, the spectral clustering. When you do the spectral clustering analysis, some of the early works is Li et al. And Lewis et al. So they are trying to prove that when you do the spectral clustering, you can do another k-means on the representation space to get the clusters. So and that's a much harder proof than this, right? Because the reason is that there's a blessing of the downstream linear classification. Basically, when you have a few labels in a downstream case and you do a linear classification, it's much easier to get the exact clusters from the representations. But when you have purely unsupervised case in the classical spectral clustering case, right? You don't have any labels whatsoever, and you get the Euclidean representations, the vector representations, and then you do another k-means on top of it. That analysis is very, very complicated. I remember this is one of the first 2 papers I read during my PhD. It was pretty tough. And the sample complexity for the downstream thing is obviously O of k. K is the dimension of the representations, just because that's the complexity of the downstream linear classification. Okay, and why this is the case? Why is it linearly separable? So now I'm using the same example here. You have this graph with 10 nodes and 3 clusters, and if you look at the eigenvectors, it's in this extremely separated, isolated cluster case, the eigenvectors are very clean. So basically, the first eigenvector is encoding the first cluster, which is just the x1, x2, x3. And the second eigenvector is encoding the second cluster, and the third one is doing the third cluster, and then the other eigenvectors are not meaningful anymore. They are just pretty much random. And then if you look at the rows of the eigenvectors, they will be just representations of the node. So basically, it's a one-hot representation, right? So basically, this guy has 1, 0, 0, 0 in some sense, and so that means it belongs to the first cluster. And this one has non-zero entries in the third entry, in the third coordinate. That means that it belongs to a third cluster. So it's really just the scaling of the one-hot embeddings of the cluster ID up to some scaling. Of course, when you really learn the representations, you are not learning exactly the eigenvector. You are learning a rotation of this, because any rotations of the rows will not change the contrastive laws, and so that's why you cannot read off this from your results. It's not like when we read the embeddings you learn. It's really simple one-hot vector. It's a rotation of the one-hot vector. So this is why the representations and then if you so in this case you can see that clearly. Because the representations are one-hot vectors, you can do any classifications with these one-hot vectors as long as the labels are consistent with the cluster ID, and anything that is consistent with cluster ID will be able to be retrieved from the one-hot vectors linearly.
Going back to your theorem, right? Your theorem has this condition which you can prove, which is k greater than 2r.
Yep.
But the k you said before, like 384.
Yep.
Right. So do you think that in reality it goes like far r is going to be much bigger?
Yep.
Than k over 2?
Yeah, that's a great question. So whether this is realistic, right? So let's say for ImageNet, let's say R is 1,000. Suppose you believe that, then you need K to be 2,000. So that's a reasonable case. But do you believe R is 1,000 for ImageNet, right? Do you have 1,000 clusters there? It depends on what's the granularity of clusters. If you believe that the granularity of the clusters is the same as the labels ImageNet, then that's reasonable. But you could also say, oh, actually, maybe every label ImageNet, there are 1,000 labels in ImageNet. Every label actually has a few subclusters. Then it becomes a little bit tricky, right? So, and in the second, I don't know how much time I have. Like in some later part of the talk, I'm going to discuss the cases where the R is really, really big, and you can still do something there, but it's a little bit more messy there. I have another 25 minutes. Sorry, yeah, thanks.
Related to mode collapse?
Like
the relation between K and R, does it determine mode collapse?
No, I think here the case to be, so the two is really just that in a bound it's easier to have a constant. So in some sense it's really K is bigger than R, and the reason is just that when you have R clusters, you need R one-hot embeddings for each of the cluster. Yeah. So, okay, so now let me talk about, maybe I should skip some of the. Okay, I do want to have these slides because this is very theoretical, and this is basically the. Okay, so why this is a linearly in the general cases why this is true, right? When you don't have this super clean isolated clusters, why you can still prove that this is a linearly separable. So I think this is the slides with the proof. Suppose you have this graph, and you want to say that the dogs and cats are separable by the representations that you learn from the spectral clustering. And suppose you basically want to represent this labeling by linear combinations of the rows of the eigenvectors. So basically you have a target labeling, which is like a bunch of ones and a bunch of zeros, and you want to say that you can multiply this matrix with a linear head such that this is true. So basically you want to find that there's an A such that the multiplication of this matrix with A is equal to this target labeling, because the rows times A is the linear classification you are doing, right? The rows are the features, and A is the linear head, and you multiply them, you get the target label. So basically, you just want to say that there exists an A such that the target labeling is equal to U times A. And why that's the case? That's because that the target label is called little u. So what you know is that the target label needs to be something that is consistent with your clustering structure, right? So you need to use that fact. And how do you encode that fact? You encode it by saying that the U transpose LU, which is the Laplacian on the vector U, which is actually, the Laplacian has this semantic meaning that is equal to the number of edges between the cats and dogs, between the two classes. And you know that this is a reasonable, the U is reasonable because it's kind of consistent with the clustering structure. That's why you know that the number of edges between dogs and cats are small. That's why you know that U transpose LU is small, right? That's assumption that you make on the target labeling you are trying to achieve. And once you make that assumption, then you know that U is in the span of the eigenvectors of L. U is in the span of the columns of UIs. And once in the span, that means that U is equal to this matrix times A. And that's it. And because this is very linear algebraic, you can tolerate all kind of like errors in a very nice way, so that you allow all kind of like a perturbation theory as well. Okay, so let me also talk a lot about this, which is also a confusing thing. So basically, many people ask me this question, like we are working with the population graph, but how do you work with the empirical situations, right? When you have the empirical graph, even you have ImageNet, you have only 1 million examples. The empirical graph looks like this. There's no whatsoever connectivities in the empirical graph, because no any two images in the ImageNet data set are augmentations of each other, unless you are really augmenting the same original image. Otherwise, there's no overlap at all. So this is the empirical graph with polynomial samples. And this is the reason why the manifold learning didn't work, because if you work with this graph, you need really a lot of samples so that you can see some connectivity here, right? And that's the fundamental reason for all the manifold learning that people have done in the last 20 years ago. What makes this work with polynomial samples? The reason is that you have a parametric representation functions, which introduce some of the complexity constraints implicitly here. So if you do non-parametric contrastive learning on this empirical graph, it's going to fail terribly because nothing is connected. And but actually, what you really do is that you do a parametric form on this empirical graph. Eventually, that's what the contrastive learning is really doing. So basically, this combination would work, non-parametric with population. This combination would work, and this combination work, but this combination wouldn't work. So theoretically, what we do is that, so you have a contrastive learning spectral clustering. So what you know is that non-parametric with spectral clustering wouldn't work because you don't have enough samples. And non-parametric with population graph works. And non-parametric with population graph on spectral clustering is the same as non-parametric population graph and contrastive learning. That's what I show in the beginning of the talk. And then we move on to this table where first you assume that the model class can implement eigenvectors, and that's how you move from non-parametric to parametric. You just assume you have expressivity so that you can parametrize those eigenvectors by functions of the images, right? So here's the parametrization. Before you have so many parameters, every image has one parameter, and now you have a function of the raw image, and the theta is the parameters. You have a finite number of parameters. So that's how you go from non-parametric to parametric. You assume this parametrization wouldn't let you lose anything. And then when you have parametric form, then the population and the empirical graph are not that different. And how do you link these two? You link these two through the loss functions. So you through the loss function concentration. So here, you are not thinking about the graph. You are only thinking about the loss function, which is which is a numerical form of the parameters and the data, and it's an expectation of some loss function, and you just apply the standard concentration inequality, VC dimension, radar marker complexity stuff, and that's how you go from here to here with actually without thinking about the graph perspective. Yeah. So. Population graph means that you have basically it's the manifold, right? It's the entire support of the distribution, right? You build this graph on the entire support of the distribution.
But then you have like a million examples.
Not a million, like you have maybe.
But you can certainly use spectral processing.
Yes, I think that's the problem with this, right? If you have a million examples, you're going to look like this, right? Right.
Million examples will look fine.
I don't think you have connectivity. The augmentation is not big enough to build any graph with a million examples. For M, sure, for MNIST, yes, but for ImageNet.
Like that. So it's not.
So it's going to be exponential, right? So because it's exponential, right? Basically, if you have exponential number of data points, sure, you can use empirical graph and non-parametric form and spectral clustering. That's fine. But you want to have a point exponential in dimension, I say.
The determinist is like whatever 800 dimensional.
I think that's just you have some smaller intrinsic dimension, maybe, right? So like you can even use 3. I think there's 4 pixels that can give you 95% accuracy for MNIST. You just need to find 4 pixels to do that, right? Okay, I only have probably 20 minutes left. So let me go to some of the other part of the talk. So this is a small continuation of the same. Okay, so the one follow-up work we have done is that you can also look at the not only the clustering structure of the embedding space, you can also look at the directions in the embedding space. And it's kind of like a second order relationship in the Euclidean space. The clustering is the first order thing, and the relationship between the clusters is a second order thing, and that captures relationship. Let me elaborate on this. So basically, what we have done is that you have this maybe let's suppose you have 4 clusters here. You have a sketch butterfly and a sketch clock and a real butterfly and a real clock, and you have this. The first order bit is you treat this as 4 separate, completely separate clusters, and then you say that if the interclass connectivity is smaller than the intraclass connectivity, then you say that the representation space you have linear separability. That's what we did just in the last hour. But you also want to kind of capture some of the relationship between the clusters. And clearly, there is a 2x2 grid here semantically. And how do you do that? And you can say that actually, if you satisfy additional assumptions in the class in the graph, if you assume that these kind of blue edges here and here and here and here, there are more blue edges than the pink edges, which is so basically pink edges have both different classes and also different styles. So if the number of pink edges is smaller number of blue edges, and that's the property of your graph, then you know that actually you can have this linear transferability where these clusters will be organized in this way, in this kind of like a structured way, so that if you do a classification for the first domain between butterfly and clock, you learn this classifier between sketch butterfly and sketch clock. The same classifier will transfer to real butterfly and real clock. So basically, it's more organized. These 4 clusters is more organized in this space. It's not going to be entirely as organized as this because this is 2D. Then that's the case. But in 3D of high dimension, you're going to have, for example, this cluster is kind of a little bit outside the wall, and this is inside the wall. But you still have one dimension that it transfers, and that dimension is the learned classifier between these 2 that will transfer to the other one. So and this can be proved theoretically with the assumption that this is true. And here there's no statistical generalization. You assume some property of the graph, and you show that the learned representations have some other transferability property. So and this is actually pretty useful. Like people we have used this for some of the empirical research as well. So okay, so I have. Yep.
Maybe you have mentioned that transferring one to the other. There are two possible directions.
Yes, the other one also works. Yes, yes, exactly. Because the assumptions here, depending on how you assume it. So the assumption here is each of the blue part is larger than the pink part. So the assumption doesn't really differentiate the two axes, right? So that's why if it works for one axis transfer in one axis, it should work for the other transfer of the other axis, right? So, but if you make some finer distinctions on the assumptions, maybe you can say this two part is bigger than the pink. I think then we'll get only one side of the transferability. So in the next 15 minutes, so let me talk about some of the more complex situations where you also consider in this contrastive learning framework the architecture's influence and also the optimizer's influence to the whole system. So so basically, what the whole last hour was about, how do you say the pre-training loss affects the downstream loss, and all the other things is kind of we're trying to kind of like say that the population versus empirical doesn't really matter as long as you have polynomial number of data points, right? So basically, the conclusion from the last hour was that you only have to think about the structure imposed by the population pre-training loss, and that's the only thing you care about. But there's some problem with this theory, which is that you found that actually if you use two different architectures, a ResNet and a vision transformer, they could have the same, very similar minimal possible pre-training loss, but still their downstream performance are still a little bit different. So the architecture still matters, even though they have the same pre-training loss. So pre-training loss is not the only thing that matters. Of course, this is a second order bet in the sense that if your pre-training loss is not good, then there's no way your downstream performance is good. But the same pre-training loss can still have different downstream performance by a few %. So that means that there's a
why you're relating the pre-training loss to how useful it is? I mean, why can't they have extremely high pre-training loss and still be very useful? Like, for example, if the pre-training task has lots of added noise to it,
yep.
And if I do it well, it's still extremely useful for downstream tasks, even though my pre-training loss is extremely high.
But I think that's just because you have a base noise error, right? But your excess pre-training loss is probably still good.
But my way is still good?
Your excess pre-training loss.
But that's not what you're measuring here.
Because we didn't have noise, right? Like, but
but you always have.
But basically, I'm saying like the conceptual. I'm trying to criticize my the previous work. So the premises is that the previous work is trying to say that pre-training loss is the only thing that matters. Or at least the previous only considers the effect of the pre-training loss. It only says that if the pre-training loss is small, then you ensure the downstream task is good. Right? It didn't say the other direction. It didn't say that that's necessity, right? It didn't say that a small pre-training loss is a necessity for downstream tasks. But it only says that if you have a small pre-training loss, it ensures that the downstream loss is small. And I'm saying that that's not enough to explain all situations, because you have the situations where two models have the same pre-training loss, but their downstream performance are different.
Yeah, I'm still. I mean, that was for a very particular architecture, right? I mean, I'm not sure. Like, why would? I mean, I'm still confused with about this relationship between training loss, pre-training loss and usefulness. I mean, for example, my pre-training just does nothing. Does nothing basically.
Yep.
Then it can have perfect training. If I'm learning representation, which is the original thing, but with some excellent predictor, then the representation is useless, even though my pre-training loss is 0. I mean, this is.
If your pre-training loss is 0, I think your representation couldn't be useless. At least under this framework, if your pre-training loss is very good, the representation should.
We'll talk about it later. And I'm a bit confused about why at all you're making this up. But
I think the way I think about it is that the previous work, the principle was to introduce some structures, introduce some kind of causalities here. And the causality I'm trying to say is a one-dimensional causality. If you minimize the pre-training loss, you should have guarantees on the downstream performance, right? So that's what I'm trying to, even though, and that's not obvious to achieve, right? Otherwise we wouldn't have the previous work. It's not obvious that you minimize the pre-training loss, you imply downstream tasks, right? So it was not obvious, but we did prove something there. And I'm trying to say that that's not the end of the world, because that's not the only factor. The pre-training loss is not the only factor. It also has other factors about from the model complexity, so on and so forth. Yep. And how do you study this, right? So you need to introduce some additional dimensions to think about, why the model architecture will come into play. Like, what's the intermediate quantities that the model architecture kind of helps? And this relates to some of the questions about the number of clusters in the graph. So basically, the previous works requires that the embedding dimension is bigger than the number of clusters in the graph. And basically, implicitly, you are assuming that the number of clusters in the graph is not very big. But what if the number of clusters in the graph is very big? Where you have so many clusters in the graph, like especially if you define the very kind of like fine-grained clusters in the graph. And this is actually heavily inspired by one of the paper by the Princeton people, and by a bunch of people. Especially like Nick Winch. So they create this example where you can have extremely a lot of number of clusters, but contrastivity still works. And the way to construct this is that you have one dimension, which is the intrinsic dimension you really care about. And this dimension is invariant to the augmentation. And you have a lot of sparse dimensions. Here, I'm going to draw in one dimension, but you can imagine there's like a 1,000 sparse dimensions. And those dimensions are where you are doing the augmentation, right? So you could have like exponential number of clusters, here, even though there are only 4. But the only dimension you care about is this dimension. And according to the, in this case, according to the previous theory, you need k to be larger than 4. But actually, if you use only a linear model, suppose you only use a linear model for the representation, for the embeddings, you only need k is 1. Meaning that if you insist that you're learning a linear model, then the only representation you can learn is you just project everything in this dimension. So basically, this is the right embeddings, where you just project everything in this dimension, and that's the only thing that matters. And how do you build a theory that can explain this? Why this is happening? So the way to think about this, the way we think about it is that because you have these additional constraints on the model family of the feature extractors, you can define a subset of possible partitions. You can kind of like introduce different kind of properties of the graph that depends on the model. So basically, we introduce this new notion called model implementable graph partition, or model implementable eigenfunctions. So not all eigenfunctions should be considered as valid, because some of them are not, all eigenfunctions or eigenvectors are considered as valid because some of them are not implementable by the linear models. For example, if you partition this thing into this structure and you use a linear model to partition, then you wouldn't be able to do it. By linear model, I mean that you don't have a threshold. And the reason is that if your output is 1 on this cluster, it should linearly extrapolate to this cluster, so it should be all 1 here. So if it's really a linear model. So this kind of like a partition wouldn't work with a linear model, and this kind of partition wouldn't work with a linear model. And the only way that it works is this kind of partitioning. So basically, the new theory is the following. So suppose R was the number of major clusters before, which is exponential in this case. And let's define R0 to be the number of major clusters that are implementable by your model class, right? So, and that's a much smaller number, at least for this case. When you have a linear model, you only have 1 implementable clusters, even though there were 4 clusters to begin with. And that's how you reduce the complexity, because the new theory says that everything depends on R0 if you use this class F for your feature extractor, for your embedding model. And sample complexity, the dimensionality, all depends on R0 but not R. And this is how the function class comes into play, because it lets you to have a smaller complexity in the sample complexity. And you can also kind of prove that for many of the, for some concrete synthetic cases, indeed R0 is much smaller than R. For a few examples in Sanxi et al. And some of the other examples we created. And you can also empirically test, what's the difference between R and R0, right? So, and you can test that, if you look at the number of partitions you can do with 10 clusters for CFAR. So there exist the 10-way partitions with the CFAR, the ResNet. But if you try to partition it into 300 clusters, it's going to be very difficult. And this is the constraint that is kind of like introduced by the ResNet, right? So even though in theory you may say, oh, actually there are 300 clusters, but the ResNet is not enough to partition them, is not expressive enough to partition the graph into 300 clusters. The ResNet is only able to partition the graph into 10 clusters, and that's why the real R0 should be 10 as opposed to 300, because it's a model-dependent quantity.
Then you won't be able to express an arbitrary is a limit, so you might not be able to perform the downstream task, right?
Yes. So then you restrict the scope of the downstream tasks as well. You say that I know what you mean. So you say that I can only solve those downstream tasks that can be that is consistent with the model implementable partitions. Right, so the partitions that are the downstream tasks that are not consistent with the model implementable partitions are not within the scope of the consideration.
How do you gain some insight into which tasks are consistent?
I don't know. Yeah, it's so I know this is a limitation here because this definition is this model implementable partitions is so complex. There's not a lot of linear algebraic structure, so it's very hard to reason about what is model implementable partitions and what is not model implementable partitions. So in some sense, I'm still on the level of like I'm introducing this concept so that at least the models can come into play in this framework, right? But how do you use this framework to reason more is kind of very hard. I agree that's a limitation.
Assumption perhaps, because it's like you're trying to have a single like a linear classifier to get all clusters, in the sense that because that would really limit things.
Oh, but no, the linear here is only an example. I really by linear I really mean a function class f. It could be a ResNet, it could be a transformer.
You can have like, if your data is well clustered in one U2B, like there can be many clusters and you can do k-means on it, and you can find the clusters, right? So I think maybe I'm a little, I'm trying to map what you said before to now, this aspect.
I'm not entirely sure which context, but maybe let's take it offline. I only have like 5 minutes maybe. Yeah, because I'm not entirely sure which level you are talking about. So basically, you have a lot of clusters in this graph, but not all clusters are partitionable. Not all clusters are implementable by the function class you are talking about. Maybe you have a ResNet which only has 100 layers, and they cannot implement all the possible partitions. So in some sense, here it's not that there's nothing that deep here because. In some sense, if you look at the proof, it's kind of a little bit like tautology in some sense. So like so basically you are basically just relating model implementable partitions to those clusters you can learn from this contrastive learning. I'm not sure whether. Yeah, maybe you can take it offline. Yep.
I was thinking if I was like finding like k r centers for that data, like why wouldn't I like be able to find the R4 centers?
But you have a lot of centers. Maybe let's take it offline because I'm not sure I'm answering the right question. Yep. So very, very quickly, maybe 2 minutes, we also found another thing, which is that, if you believe in the theory before, you would say that conditional same partitioning laws, a simpler class will have fewer model implementable clusters, and you should have better performance, assuming that your function class is still realizable. Because the more restrictions you have, the smaller number of clusters that can be implementable, so that the R0 will be smaller, and then you should have better performance. But then empirically, actually, even conditional same partitioning laws, if you have bigger architecture, it always gives you better performance. But this is in some sense very similar, reminiscent of the. I have some plots here which we can skip. So basically, this is very reminiscent to what happens with the implicit biases in the deep learning theory. So you have bigger architecture and you have better generalization in some sense. And here, there's no statistical part of the generalization. This is really transferability from the partitioning laws to the downstream tasks, but still the same thing, right? You have a bigger architecture, you are more expressive, and in theory, your R0 should be bigger because you can implement more clusters, and somehow the performance is actually better. So I think the answer to this is that just the simpler doesn't really mean that fewer parameters. You have more parameters, but the model can be simpler. And the reason is just that this is exactly the same phenomenon as in supervised learning. So the models learn with more parameters actually can be simpler under other complexity measures. I guess this is the recurring theme in all of the deep learning implicit bias literature in deep learning. So basically, you have this maybe two global minimum and maybe let's look at this. So you have a larger architecture and you have a smaller architecture, and you have a simplicity implicit bias, and you have a family of global minimum, and even though you have a larger architecture, but actually the minimizer of the simplicity bias might be more simple than the minimizer of the smaller architecture. Just actually, that's by definition always the case, right? If you have some implicit bias to encourage simplicity, the large architecture will give you a simpler model compared to the smaller architecture. Just because this the simplest model within a large architecture is actually simpler than the simplest model within a smaller architecture. And here the only difference is that this is about it's on the population loss, and it's about transferability from the pre-training loss to the downstream task. So it's not about statistical sample complexity. And you can also show the same thing with the population pre-training. You can say that if you run SGD and get a global minimum, you can converge to the global minimum with the minimum hashing. And actually here some of the math is actually easier because you have a better loss functions in some sense, like because the especially if you look at the large language model loss, it's even cleaner. So and you can show that the trace of the hashing actually correlates with the downstream performance. The trace of the hashing will be the simplicity bias in some sense. Okay, anyway, I'm out of time, so I get just a very quick summary. So contrastive loss is close to spectral clustering, is equivalent to spectral clustering in a positive paragraph. And if you learn the constructive representations on this kind of structured situations, you can disentangle the class and domain information and have this transferability. And then we discussed a little bit about the inductive bias of the architecture. If you have a smaller architecture, then only the model implementable clusters matter. And also the implicit bias of the optimizers will encourage a flatter local minimum in the self-suppressed loss, and this flatness seems to correlate with the performance. I guess some of the open questions. This was so how does the type of augmentations affect the graph clusterability? This is one of the questions raised. I don't have an answer to that. It's just the paper only answers that there is. It only says that this is the intermediate quantity you care about, right? Because before you're asking about how does data augmentation affects my downstream performance, and now you only need to ask the question, how does augmentation affect the graph's clusterability, right? And do contrast representations have other nice properties, right? So we talk about the transferability, but actually, what if the graph has a hierarchical cluster? Then maybe you can use the same theory to show that the representation you learn actually captures the hierarchical structures as well. I spend a lot of time on this because this is my former advisor's work. I was trying to turn the ARV the sparsest cut, kind of like the L2 square constraints into the empirical thing. So basically, you can say, okay, I'm trying to do the sparsest cut, right? So like in the ARV, you have this additional inequalities you can restrict it to make the separation of the clusters much better than spectral clustering. So it's a stronger clustering algorithm, and you can actually implement it. But we tried it; it didn't work out very well so far. But it could be an empirical issue, and we don't have the concrete result on how the architecture affects the model implementable clusters, even though there's just some framework that allows you to think about that. And another probably bigger dimension is how do you understand contrastive learning for texts? This is actually very much used these days in empirically as a motivated for RAG, retrieval augmented generation. And there, the text has some different kind of like the structure in the data is a little bit different. So and the positive pair is also a little bit different. People are using headers and a document as the contrastive as the positive pair in most of the cases. And also there, the clustering structure is probably less justified compared to vision. It's kind of hard for you to claim that you have very clean clustering structure in the text space. And maybe broader questions about pre-training, I guess other large language model objectives. We have done some works on latent Markov structure, but the HLM space, but it's kind of pretty challenging once you look at next word prediction problem, and also other adaptation methods. I guess fine tuning, in context learning, zero shot learning. So why the pre-training can help in those cases where you are. For downstream tasks, you are using different ways to solve the downstream tasks. Thanks so much.
Can you say anything about how that contrastive losses besides the quadratic one?
So let me just let's see. Hopefully I can recover this. So the most this is called sim-clear. What it does is that you have fx, so it's some exponential of fx times fx plus. X and x plus is a positive pair. And then you say below you have exponential fx transpose fx plus, and plus a sum of exponential fx transpose fxj, where this is j from 1 to maybe k, where x and xj are negative pairs. So you in this loss function, you have one positive pair and a lot of k negative pairs. Maybe k is like 1,000, 5,000, something like that. And you have this loss, which is kind of like, in some sense, you are trying to do a classification. This is actually the logistic loss when you do a classification between positive pairs and negative pairs. You are trying to identify which is the x plus among all the pairs you are given. And you can, just a simple math will tell you that the bigger this is, the smaller the loss, and the smaller this is, the bigger the loss. So maybe I need a log here, and maybe I need a negative here, something like this.
Yeah, I meant for that loss or any other. Can you say something about the connection to the spectral?
I can't, just because this is kind of like you are using logistic. The one way I think about this is you are using logistic loss for matrix factorization, right? When you do spectral clustering, you are using the square loss for matrix factorization. And when you use logistic loss for matrix factorization, just all the linear algebraic stuff just breaks, and I don't know how to do it. Yeah.
I think the related question is because, like, if you're not considering like k negative example, this is like another way to essentially look at contrastive losses. It's like trying to do like metric, it's also connected to metric learning. How you learn metric from like triplet comparisons, right? You give a head A and you ask is B closer to A or C closer to A. Here it's like you give a list, a head X, and you're asking which of these is closest, and you take the closest example as the positive pair and everything else as the negative pair. So it's like there is a continuous analog of thinking about like what this is learning, but in a sense you don't need to have necessarily a graph. You can have a connected graph with a weighted graph, right? So I mean we can talk.
Yep.
Just to, as a comment to the question, right, there's a paper by Young Nichols group, right, in New York, saying that contrastive and non-contrastive self-supervised learning recover global and local spectral embedding methods. Right? So they make connections for many contrastive and non-contrastive losses.
But the connection is, depending on how you define the connection. I think the hardest part is that, let's say just that you have there's no contrastive learning, just that there's only a matrix. You want to factorize the matrix. You want to get the eigenvectors of the matrix, but you are using a weird loss function, which is like something like this. So
Spectral clustering specifically.
Yeah, but without that spectral clustering machinery, you cannot talk about the linear downstream, the linear separability of the downstream tasks. That part is really heavily linear algebraic. Why you can the representation you learn are linearly separable in the downstream task. That requires this. You are in the eigenspace, the Laplacian form. You are in the eigenspace of the eigenvector, so on and so forth. At least I don't know how to replace that part so far.